Good morning, everyone. Welcome back to day 5 of the Linley Group's Fall Processor Conference. For any of those of you who don't know me, I'm Mike Demler. I'm a senior analyst with the Linley Group. I'll be moderating our second session today on edge AI processing. The format will be, we'll have 3 speakers. Each presentation will be 20 minutes, and we'll have 10 minutes for audience Q&A. So hopefully you're all familiar with the platform. Please go ahead and enter your questions anytime, and we'll go through those at the end of each presentation. After the 3 presentations this morning, we'll have a break, and then another session later on to follow that. So let me introduce our first speaker. Cheng Wang will be speaking to us today. I know you see Jeff Tate on our agenda. Jeff will be available later on in the breakout session. But Cheng will be presenting to us again. He's a VP of Software Architecture at FlexLogic, a co-founder of the company. Previously worked as a VLSI designer at Zoran. And one of your accomplishments that I'm jealous of is you won the Best Paper Award at ISSCC a few years ago. So that was a great accomplishment as well. So welcome back to the conference, Cheng.
Good morning, everyone, and welcome back to my talk. Yeah, thanks, Mike, for the great introduction. Yeah, ISSCC was for my PhD days, and I look forward to going back to those someday. Following our successful launch of our InferX X1 chip last week, today, I'd like to focus primarily more on the software and the PCIe card as a continuation of the discussion of our edge inference family. As you will see, we have a fairly low power card with TDP of less than 20 watt and actual power much lower than that. So let's go ahead and dive in. So last week, we had a quick just a quick recap of last week. Last week, we discussed a few winning properties of the InferX X1 silicon. Primarily this focuses onto a higher throughput per cost. Cost, let it be area, let it be components, let it be power. Okay, and we achieve this high throughput at a low latency, which primarily is batch equals 1 for edge inference applications. In fact, compared to the NVIDIA Xavier NX, we basically performs faster than they do at batch of 1 for all the models that the customers have benchmarked, as well as a few of the key benchmarks that we care about and the customers care about. And the customers don't just want high throughput and low latency, they want it at a high accuracy, a high numerical accuracy, let it be floating point or integer with no pruning of the models, of course, and also a high accuracy from a high accuracy model, a large model, it's generally those, and running on high resolution, multiple megapixel of images. And all those things generally requires a hardware of pretty high horsepower. But what X1 is able to deliver is we've optimized all of these properties, yet on a silicon that is very small, a very very small form factor and low power as well. In fact, the whole silicon, as you saw last week, was just 54 millimeters squared, even though we're using TSMC 16 nanometer, with the worst case TDP of 7 to 13 watts. Obviously, the current, based on your model, the typical power is much lower, but TDP is what you design the components for. Yeah.
Cheng, if I just cut in for a second. Your camera is a little bit going over the top of your head, so if you could maybe point it.
I'm sorry.
We can see your whole, there we go, that's a little bit better. Thanks.
It is better? Yeah, sorry. Yeah. Sorry to be showing you my forehead here.
Yeah.
So, sorry about that. Yeah, well, most of this chip is a reconfigurable tensor processor, as we saw last week. And that's where our secret sauce lies, and that ties up to a NOC. And that goes to the rest of our interface components for the most part, and they're very simple and small interface components. We got a single LPDDR4X, which is just 32 bits, and we have just 4 lanes of PCI Express. So all of this result in compact package because we don't have that many pins to pin out. The chip itself is not very big, and you will see that it results in a pretty simple board as well. And we'll first cover the software components because that's what actually a lot of customers care about. So in terms of how the software attempts to fully utilize the hardware, this is a very simplified diagram, as I've covered last week, of where we have a number of TPUs. This shows just 4, but in reality we have 16 sets of these, so it turns into 64. And the compiler basically decides for each layer how to best use these TPUs, where to take the L2s from, how to route the L2s to stream through the TPUs to another set of L2s. And then it reconfigures itself. Now, keep in mind, for a large model like megapixel YOLO, we're looking at, say 10 frames per second with about 100+ layers per inference. You're reconfiguring probably once every milliseconds or so. So by spending 4 microseconds, which is a fraction of a percent to reconfiguration, the overhead is very acceptable. But in return, what you get is a completely rewired set of max and the data path. So basically, once the reconfiguration is done, it looks just like the ASIC has reconfigured itself. In this case, say layer 1, it makes more sense to go through 3 TPUs instead of 1 between accesses to memory. So the compiler just requests that and the router routes it. But there's no NOC, there's no packet-based switching, just direct point-to-point connections. Basically, once the configuration is done, it looks and performs just like an ASIC. And that's where a lot of our efficiencies come from. And speaking of efficiency, we compare with Tesla T4 last week, where it's something that is about an order of magnitude bigger than we are. They're both pure accelerators. They're about 10 times our size with 10 times the DRAM bandwidth. And you will expect this order of magnitude a trend to hold in the performance, but it doesn't. Even in the model that's coming from NVIDIA themselves and optimized for the latest TensorRT environment, they've only managed to perform about 3 times better than we have. And on customer models that don't have the luxury of being tuned and optimized by NVIDIA every time, we are looking at a much closer gap, anywhere from a factor of 2, or in some cases, we're even outperforming the Tesla T4. So again, this is something that is an order of magnitude larger than we are, with something like 16 times the TOPS. So TOPS does not correlate to throughput, especially not for our architecture. So to show this picture a little bit more clearly, let's normalize them by dividing the throughput by cost. Let that cost just be represented by millimeter squared, but as I've mentioned, everything is roughly an order of magnitude larger in the T4. So on this chart, it's pretty clear we're anywhere from 3 to 18 times more efficient than what the GPU-based solution is able to deliver. And more impressively, all of this computational efficiency is automatically realized by the compiler. So let's jump into that very quickly. The InferX software is actually very easy to use. There's all stuff happening in the background, but as an input, we just take an open source, high-level, non-hardware dependent representation of the neural network model. Let it be a TF Lite or Onyx. These are just protobufs. And we intentionally did not want to support TensorFlow in general, because that's more of a Python-based language, and it just makes the description much harder to parse into our compiler. And we find that most customers actually can have a relatively easy time generating one of these 2 formats, and that gives a very clean deliverable to us. Our compiler then takes this model and then looks at the available X1 resources, and then generates a binary executable. Of course, this is not for x86. A binary executable executes on our own silicon. There's almost no involvement from the user once they have provided the model to us. And then it goes into our runtime environment by the time showtime comes. And the runtime is very straightforward as well. It's able to take an input stream, but let it be a library of images if you're just doing some pre-collected data, or you can directly take it from a live feed, such as a camera. And the user specifies which compiled model, or like which binary I want to associate with the input stream. And the InferX runtime and the driver just takes it from there. It will load data onto the hardware. It controls the hardware to run the inferencing, and the result is sent back to the host to be displayed or processed based on how you want to view them. And our compiler really takes this by looking at each layer of the model. For example, YOLO v3 has like something like over 100 layers and something like 80 conv2D layers. And then each layer has its input features, its output features, its window size. It's a 3x3, 1x1, and we're doing Winograd. And also the stride, right? Stride of 2, stride of 1. And all of these things are factors into the compiler when it determines how to optimally configure the 64 TPUs to get the maximum throughput. And as we've seen on the previous slides, this is just an example mapping of the L2 allocation, the TPU mapping, how many to have in series, how many to have in parallel, and where does the memory come from, let it be L2 or DMA, and where does it go to, whether it's L2 or DMA, and also how are the weights to be allocated. All those things are done by the compiler automatically. And these are just some of the simpler optimizations that the compiler do, assuming each layer actually maps to a unique configuration during execution. So you will run layers 1 as one configuration and then reconfigures itself, run layer 2, reconfigures itself. But the compiler actually can take it a bit further and see which layers it makes sense to fuse into one configuration. And we call this deep layer fusion. And there are many benefits to doing so. First, it can eliminate some of these larger intermediate activations. Like there are maybe intermediate activations that need not be stored as a shortcut for later. And those, if can be fused, can eliminate a lot of the activation read-write. And especially these larger activations often have a hard time fitting into L2 SRAMs. We have to write them out to DRAM. So it can actually eliminate a lot of DRAM traffic, eliminate a lot of bandwidth bottleneck, and also power caused by DRAM. And also another benefit the compiler can realize is that it can use its fusion to fill up some of the unused computational resources. Because say like layer 2 may be a very large layer, and we're unable to perfectly use all 64 TPUs based on, say each instance needs 6 TPUs. So there may be 2 empty ones for every 8 instances of TPUs. And we can use those 2 free instances to map, say, layer 3, because a lot of times the subsequent layers, whether before or after, may not require as much TPU resources as some of these bigger layers. So the compiler takes all these things into consideration when it does its optimizations. And then when the binary executable has been generated, it is fed into the X1 by runtime, which invokes the X1 driver. And of course, there's an LPDDR attached to the X1 silicon on the card. So the host is then able to use a simple API to just first load the precompiled binary onto the DRAM, and then run a model by giving the input pointer and tell it where the output pointer is. And the X1's DMA will then just DMA in the image, perform the inference, and then send the output back to the host. And multiple models executable can be stored on silicon, on the DRAM at the same time. And so the host can then provide another image specifying, do I want to run the same model on this image, or do I want to run a different model on this image? Okay. And in essence, the fundamental commands for compilation and inference is just one key command. Obviously, there are a lot of parameters that you can tune, but for compilation, you're loading the Onyx model. The compiler knows what the InferX X1 architecture has in terms of resources, and it just outputs an MX compiler format. And running inference, it's similar. Of course, if you have multiple models you want to load at a time, you want to load them first before you provide the input stream. But really, it is extremely simple for the user to get up and running. In terms of schedule, we're bringing up YOLO v3 right now through our compiler framework, and we expect it to demonstrate it very soon in the coming weeks. It's got more than 100 layers, but we are getting there very fast. Then we will be bringing up a few of our lead customers' models. So by Q1, we should have an advanced compiler that can handle models that are commonly used, by a lot of the models out there, but also is already supported by our initial set of models. So it should cover a good amount of popular models out there. And then initial support is, of course, for mostly Unix-based operating systems. And we'll have a more general compiler availability in Q2 with production hardware and, of course, expanded operator support. but realistically, we'll be adding operator support all the time as innovation continues. So now let's move on to the PCIe card. Okay, our InferX X1P1 PCIe board has just a single X1 chip on it. It's working today in servers in our office and it's running neural network layers. And as I mentioned, we're working on bringing up the full YOLO v3 demo now. And you see there's a lot of components on here that seems to be missing. Well, those were actually debug components and headers that we used for initial chip bring up. This is our Rev A board, and of course our Rev A0 silicon. And we're very proud to be bringing Rev A of everything into production. Now, X1P1 is the same form factor as Tesla T4. It's a half height, half length card, but we fit into more slots because we only use by 4 slots of PCIe. And we're working with lead customers now, and we expect to sample this very soon to customers that have volume, customers that have volume applications in Q1, and we'll have production in Q2. And if you remember the benchmarks, this board delivers YOLO with about 1/3 the performance of T4, and of course much higher for a lot of customer models. And you'll see that our pricing is a lot lower than 1/3 of T4. And we're starting design now on another PCIe board with the same size, and we're still debating on the connector size, let it be 5x8 or by 16. But we will stuff 4 X1s on there, and each with their own DRAMs attached to it. The TDP for this will be larger, but will be less than 75 watts, and we expect to sample this middle of next year with production later next year. And in the same time, we're also considering another very interesting form factor, which is the M2 board. We're starting the design with the 22mm wide M2 board with a similar schedule as the X1P4. The TDP for this is 19 watts, but obviously the actual power is much lower depending on the model. And it's still a very good fit for PCs and laptops or even edge servers and embedded systems. Now, both of our new PCIe boards will be cheaper than the Tesla T4, and they can fit into any slot. Even if you factor in for performance, we're cheaper by a pretty substantial amount. And this is primarily because we want to expand the use of high performance inferencing to an even lower price point and even more applications. Server customers tell us, that X1P1 should be in especially high demand because a lot of people simply cannot consider $1,000 cards, into their servers just to do accelerated inferencing. Our X1 can deliver a lot more throughput per dollar than the T4. Let's look at it graphically. We are looking at about 1/4 of the price. Yet our YOLO can run at about 1/3 of the T4's throughput. And that's just from, the best case models from NVIDIA, because this benchmark comes from NVIDIA themselves. And realistically for customer models, we're anywhere from 1/2 of the T4's performance to be up to 2x of their performance. So really in terms of performance per dollar, we are substantially higher than what the T4 is able to deliver, anywhere from 30% to about 8x. And then for the X1P4, it has a little bit more performance than YOLO v3 compared to the T4 at about 1/2 of the price. And then for other models, we go up to 8 to 10x of their throughputs. T4 does have better latency at batch of 1, but there are many applications where X1P4's price performance will be a lot more attractive than the T4's. And also allow us to fit into more slots than ever before. And to make it an even sweeter deal for customers that do not need as much performance as our highest end parts, the lower speed frequency bins allow the customers to take advantage of an even lower entrance price point. And that pretty much wraps up my talk this time. So if you really have a volume application, 1,000 units or more per year, or you're starting prototyping your model, we really like to show you how fast your model can run through our X1 flow. So really contact Andy, our sales VP, send us your models, TF Lite or Onyx, and we can typically show you results within a few days. So thanks, I'll take questions now.
Thank you, Cheng.
Yeah.
You can go ahead and turn off your screen sharing, and we'll start the Q&A. We've got couple questions coming in. Encourage any of the other attendees, go ahead and enter your question in the Q&A box. So let me start. You mentioned, you made a comment about how it's difficult to measure performance or compare performance based on TOPS, and we've heard a lot about that. But you said something about it being particular to your architecture. What is it specifically about your architecture that makes that especially misleading?
Oh yeah, so I think a lot of GPUs and CPUs, their TOPS comes from assuming computation every cycle. Obviously, the maximum TOPS is if every cycle you're doing useful work through your Mac clusters. But obviously, in most instruction-based architectures, it's very difficult to get to that level of peak efficiency. In fact, you'll be very good if you're doing Mac once every 3 instructions, and that automatically cuts your peak top by a factor of 3. But in our case, we're not running any instructions, right? Once the configuration is wired, so our overhead is not in instruction, our overhead is in configuration time. But our configuration time is specially designed to be a fraction of a %. But once that configuration time has been spent, we are looking at basically an ASIC fabric, right? There is no overhead of instruction decode. There is no assembly. There is no instructions anymore, right? It's wired to run one thing until it's rewired to run something else. And I think that's one of the fundamental differences, because if you look at ASIC, let it be a Mac array or whatever, there's generally not this kind of overhead when it comes to theoretical top versus realized top, because they can use useful work, they can do useful work every cycle, as opposed to an instruction-based architecture. So I think that's what really a lot of this comes from.
Yeah. Okay, that's an interesting point. And so the interaction with the host is only at the beginning to initiate the computational graph, or for any other configuration between?
So the instruction with the host comes at 2 places. First, you got to initialize the DRAM with your model, right? The model, the binary gets dumped onto DRAM because it runs from DRAM. And then instruction from the host really comes to just the input frame and the output frame. But in cases, say, the X1P4 comes along and we want to slice the model into 4 quarters, the output for each model becomes the output of the quarter of the model. So, but in between, there is no interactions with the host. The host simply gets the output of the model, let it be the output of a complete model in a single X1 case, or the output of a fractional model in the multi-X1 case.
Okay, and then it seemed like that's pretty simple. Are there any particular requirements for the host? It could be an Intel or a ARM processor, anything there?
Right now, we've brought it up on both Intel and AMD processors. We have not ventured into ARMs yet, but I don't see any issues why this shouldn't be. It's just a matter of driver development, and our driver is actually quite simple.
Okay, good.
And we had to use AMD to use Gen 4, of course.
So let's take some of the questions from the audience. You compared it to the Tesla T4 question now with the new Ampere architecture. Are you doing any comparisons with that? That's pretty new.
I have not looked into the, well, no, not yet, but I could look into this after the meeting and get back to whoever is asking that question. Yeah.
Breakout session. And then there was a comment there, I just posed a question about the power limit on the M2 modules. Are you exceeding the PCI specification with that?
Of course not. In fact, our driver can be specified to go no more than any power limit. So, it's a matter of how slow do we want to run, and also how much do we want to throttle. But the M.2 can go into a ton of form factors, right? And say we're going to a laptop, there's no way they're going to want 19 watts, right? But that's just if you let it run unhinged, right? And of course, it comes into a closed loop feedback with the driver on what's acceptable. And of course, the limit will also impact performance, but that comes with power. Yeah.
Got it. Then there was a question about your target markets. I mean, I think pretty much anything edge AI. I mean, not maybe the ultra low power, but
yeah, not the ultra low power, obviously, right? On the higher end, we are looking at edge servers, but also, a lot of surveillance, robotics, embedded systems that are not limited to milliwatts, but single digit watts. Also low double digit watts can find this to be very attractive, of course. It's primarily a power gain, obviously, and cost. But cost, everybody wanted to be free. We just make it as close to free as possible.
Okay, I just want to remind our other panelists to go ahead and keep their mics and cameras off while we're in this session. So David, yes, thank you. Question then from the audience: you discussed chaining the operations through the memory. Well, is this through the LPDDR or through the on-chip memory? That's the first question.
Yes. So when we do chaining of operations, it is through the LPDDR. So the next chip will route through PCIe into the LPDDR and then go back out. Yes.
Okay. And then the question was, if it was a single memory bank, or can you? I'm not sure what that means. Can you accommodate all with the TPU read-write performance? I'm not sure what all means there.
I think the audience may be concerned about memory bandwidth when we chaining, but the reality is a tiny fraction of the memory bandwidth come from the input and the output tensors of the model. Even if we slice the model by 4, that still holds. Most of the memory bandwidth is used to load configuration data, load weights data, and read and write intermediate activations.
Sure. Right. Okay. Then another question. I think you had this comparison in the talk last week about comparing to other startups like Blaze.
Oh yeah, I had a slide on that last week.
The comparison there, I think you had lower cost.
Lower cost and better power even for our lowest, lower cost and better performance even for our lowest performing part at 533 megahertz. Yes.
Right.
Yeah. Right. And really the 533. The 533 is meant as to be at especially low price point to those that are very cost sensitive, obviously.
Right, but there is a difference that they have a CPU built into their chip. And
of course, they're not a pure accelerator like the T4 or the X1, exactly.
Right. Question on the model parallelism: do the outputs of the various slices go up to the CPU cores? And I think we've answered that. Yeah. You don't have any CPU.
They don't need to. Yeah, it is a DMA.
Okay. Right. Okay. About the 21 millimeter squared package, does it fit in the M2 format, which is 22 millimeters wide?
Of course.
I think that was asked and answered right there. Okay. I had a question then about benchmarking, and you're doing the comparisons to NVIDIA. Are you looking at MLPerf and submitting any scores there?
We are, but we have not submitted them yet. The primary reason for that is, I don't want to say that it's a little bit politicized of a process, but it seems like MLPerf's benchmark are somewhat politicized by the three big companies targeting what they care about. And I'm not sure how much of our customers are running things like Inception and ResNet. So when we get those benchmarks, we will provide them. But the main thing is, it seems like the models that are there now is not directly what the customers that we are looking at are looking for. So in the beginning, we were very involved with following their benchmark release, and then we realized that it's kind of been politicized, and we haven't been as enthusiastic about submitting their benchmark as a result of it. But yeah, we'll get to it, but it's just not our highest priority right now. Yeah.
Sure, understood. Time to get out into production.
Yeah, really.
Well, thanks, Cheng, and good to have you presenting again. And anybody has more questions I couldn't get to can talk to you in the breakout session later today.
Okay, sure. Thanks a lot, Mike.
Thank you.